Today I want to talk about the design process and the success and failure that goes with it. It's really important to understand your role as a mechanical designer. What do you bring to the table for your boss or your customer or your client? First of all, it's important you understand what the device needs to do. You are the expert. Not only do you need to establish what the values of the performance specs are, but you also need to establish what kinds of performance specs you're dealing with. You need to generate concepts that are exciting and revolutionary. You need to prove that the device you've designed meets the performance specs in the worst case scenario. Ideally, you want to do this analytically and prove that the device meets the performance specs without actually having built the machine. Doing this and conveying these things to your boss or your customer greatly enhances your role and enhances your value to them. I want to introduce two words, failure and design flaw. Failure is a loss of intended function. That's when something breaks. This failure, any design that you come up with can be made to fail if the performance specs of the part have been exceeded. A design flaw is a different thing. It's a mistake that the designer's made at some step in the design process. I'll give you some examples. The World Trade Center towers were designed in the 1970s to withstand the impact of a fully loaded Boeing 707. That was one performance spec for the building. Obviously, each tower was hit with similar aircraft. Each building withstood the initial impact and satisfied the performance spec. While many died in the end in this terrorist attack, the buildings each one stood for nearly an hour and allowed many tens of thousands of people to evacuate. It saved many tens of thousands of lives. Obviously, in the end, since the buildings collapsed, there was a failure. But this was due to the intensity and size of the fire, that it exceeded any reasonable expectation of that performance spec. Here's a design flaw that happened to myself. This was a Craftsman lawnmower that I bought. Very soon after I bought it, the wheel fell off because the designer had used a plastic bearing. This bearing just collapsed and the wheel fell off. This is torturing your customer with the design flaw. This is something that you don't want to do. Under no reasonable condition would I think a performance spec would be for this bearing to last for 6 months. Another design flaw example happened when I had a Cadillac. This is actually a picture of a big block Chevy, which this one has a cast iron block coupled with an aluminum head and an aluminum intake. This is not so bad, but the Cadillac that I had an aluminum block with cast iron heads and an aluminum intake. The aluminum, being different than the cast iron, would expand at a much different rate, and the cast iron heads would float up and down and away from the aluminum intake, creating a gap, as sort of like what he's showing here. And this design flaw caused intake manifold leaks in the Cadillac. Cadillac decided to pass along the cost of repairing this design flaw to the customers and did not back the product. So let's put it into perspective for the mechanical designer. The mechanical designer has to be mentally tough and understand that the device, the machine that he's built and designed, could fail if it's been overloaded, if the performance specs have been exceeded. This should be differentiated from a design flaw, which is a mistake that the designer has made. And this can happen when a device fails, even though its performance specs have not been exceeded. For example, the lawnmower that I showed you, the wheel, the plastic bearing, lasted only 6 months, and this is surely not as long as the designer had hoped it would last. And for the Cadillac engine, the material incompatibility there is a clear design flaw. There's just no way that the cast iron and the aluminum should have been coupled together in that geometry. Had the engine been made all of aluminum, then it would have expanded and contracted in a reasonable way, and that design flaw would have been averted. At this time, I would like to introduce to you the design process as shown in Shigley's 9th edition of Mechanical Engineering Design. Shown are 6 steps: identification of need, definition of problem is where you set the performance specs, synthesis is where you generate your concepts, analysis and optimization of the down-selected concepts, and then finally evaluation of your design. An extra step shown is presentation. You actually, in the real world, you have to present at each step of the way. You do not progress to the next step until you've shown your boss or your customer the results of the current step. In the real world, this last step, presentation, you're ready for production at that point. So I would say to think of the design process in this way, a 6-step process where the last step is that your design is ready for production. But going back to the first step, identification of need. This is a very creative step, and you want to say in the plainest terms what is needed. Here's some examples. Think about 2 plates where there's a lap joint. Suppose there's a need to bolt these 2 plates together. Yes, if you're given the force, the performance spec of the force, and the material and geometry of the plates, yes, you could design the bolted joint. Let's think of the need in a slightly different way. Instead of saying bolt, let's say there's a need to fasten these 2 plates together at their lap joint. This is a tremendously different need and opens up a whole lot of other possibilities, since bolting is not the only option you have. You could weld or epoxy these plates together. So if you were to be presented by your boss with the need to bolt 2 plates together, you could say, do you want me to only bolt these plates together, or can I fasten them in another way? In other words, broaden in his mind what the need is. Another example where you increase your value to your boss or your customer. Let's consider another need. Consider there is a need to get a bomb disposal robot into the back of an armored personnel carrier without endangering the soldier inside. Notice that I used the word get. I could have used the word lift. If I use the word lift, that may put me down a path where I end up with a lift. Here's the robot sitting on such a lift, which actually is one of the concepts. Here the robot is being lifted into the armored personnel carrier. The person you see is actually the machinist. So, when you identify your need, make sure that you use very broad terms in your need. Get being a better word than lift. As the design evolves, you may end up calling the design a lift or a ramp, depending on what the design starts to look like. But in the early phase, it's important to use the simplest words. The next step in the design process is the definition of problem step. This is where you set the performance specs. It's a very analytical step because you're establishing all of the things you should be worrying about. You want to treat the design as a black box. So no matter what the design ends up looking like, you're establishing what the device must do. This defines what success is. You define what success is. For example, in the lift, consider that we're going to lift 600 pounds from 3 foot out, 3 foot down, and we're going to do it in 15 seconds. You can sort of figure that from these numbers, it's going to take about a half a horsepower to get the job done. These are just some of the performance specs. When establishing your performance specs, it's important to consider all of the things that you need to worry about because you are the responsible person. I put together a list, a very large list of design considerations. For example, do I need performance spec for product safety? Lots of times product safety is established by sending the product you've designed to a third party called, for example, Underwriters Laboratories. This would be a nationally recognized testing lab. It's a third party, it's not the consumer and it's not you, and then they will analyze your device and make sure that it's safe. And when they say it's safe, then you can sell your product as a UL listed product. UL will investigate your product based on a code. It's important very early in the design process to know what codes that you want your product to adhere to. For example, I've dealt a lot in robot safety. And Underwriters Laboratories will evaluate a robot based upon, for example, a UL 1740. That is a code. Code should be differentiated from a standard. A standard establishes an industry-wide definition for something. It creates a uniform market and an opportunity for competition. For example, ANSI establishes the standard for threads for screws. So if my company makes a 3/8 16 screw, it will mate with the nut that your company makes a 3/8 16 nut. Or if my company makes a certain gear from the American Gear Manufacturers Association standard, and your company makes a mating gear, then the two gears will mate. Or if our two companies make, say, size 23 servo motors that follow the NEMA standard, the National Electronics Manufacturers Association standard, then our servo motors can compete against one another in the market. Or my device, I may need to put a USB port on my device, and if I follow the USB standard, then my device can communicate with any computer. So basically, standard permits interoperability between products from two different companies, creates a good market. This is differentiated from a code, as I had mentioned. A code establishes a requirement for a device to be sold. It could be a legal requirement, either criminally legal or civilly legal. For example, the Federal Communications Commission puts legal requirements on you to make sure that your device does not emit any kind of electromagnetic interference for things like pacemakers or around airports to interfere with the airport electronics. I don't think I can overstate the importance of understanding standards and codes as they apply to your design. This is a very difficult and challenging area for you as you get out into industry. In order to avert design flaws later in the design, it's very important to get standards and codes into the design process as early as possible. If you understand standards and codes, your value to your boss or your customer is greatly enhanced. Other traditional things that you may need to establish a performance spec for include overall cost, overall weight, and overall size. You may want to consider or establish what the intended life of the product is. You may want to think about how much the product can deflect or distort, or how much flexibility is in the product. You may want to worry about or establish what the worst case stress conditions are, and also establish what the overall factor of safety is for your device. You may want to establish some functionality performance specs. You may want to think about accuracy and repeatability, as well as the tolerances of the individual parts. You may want to think about what the efficiency is of your device. You may want to think about establishing a spec for how easy it is to use, how easy it is to maintain, and how often you need to maintain it. You may want to think about establishing a performance spec for how easy it is to make. You may want to think about a load rating, how much it can hold or lift. You may want to think about a workspace rating, how big a workspace that it could work in, how fast it needs to go, and how much power. You may want to think about establishing a spec for controllability. How much input would it take to get a desired output? How reliable do you want your device to be? How much lubrication? If you have some surfaces that rub against one another, you may want to establish a wear rating. You may want to establish how loud it can be, a noise limit. You may want to establish some material compatibility issues, like avoiding things like aluminum and stainless steel, which start to act like a battery when they're connected together. I've already spoken about thermal compatibility, when you have things that expand and contract at different rates. Environmental compatibility is a consideration where you may have a corrosive environment. Sustainability is another keyword right now, a buzzword that's about, which has to do with how the earth can sustain the human race. Operator compatibility is also sometimes something to worry about, where the operator may not use your device as intended. I remember making a very sensitive sensor that an operator ended up using as a hammer, which destroyed it. Additional considerations. What does it look like? Obviously, make sure it serves a useful purpose. Is the thing marketable? What about lead times for some important components and also documentation? You need to have a user manual and a maintenance manual, among other things. As you go into part-specific things, you need to worry about what kind of material you're using. What's the shape and size or the geometry of the material of the part? And how are you going to make the part? And returning back to our example of the robot lift specs, it's important to know that you do establish these specs, but you end up at the end of the day proposing them to your boss or to your customer. And all of you need to agree on these specs. It's important that you understand that, because remember, your success as a designer is fulfilled when your design satisfies these specs. In my particular example, the customer and I agreed that the robot lift needed to lift 600 pounds so that it could lift the robot together with a soldier in his bomb suit if necessary. And then when my lift actually did this, then that established my success. The next step of the design process is the synthesis step. This is where you brainstorm your concepts. It's a very creative step. This is where you come up with some wild ideas, and a lot of times these wild ideas aspects of them will find themselves into the final product. In our example of the lift, actually the first concept is a ramp. And you see the ramp here where the weights simulate the robot sitting on the ramp, and in the ramp the robot slides up this part, and then the whole thing tilts over and slides into the simulated tank. The second concept I call the hoist lift. This is where we have a hoist where the strap pulls the lift up and pulls the robot into the simulated tank. In case the strap breaks, we've developed a damper in the concept here, which would dampen the fall of the lift of the 600 pounds if the strap breaks. The third concept is the geared lift. In this situation, we've got an electric motor that drives the first stage worm box, which drives a second stage worm, which drives a third stage spur reduction, which drives the lift. One of the central themes I've tried to emphasize today is how important it is for you as a designer to explore concepts and to do these things without actually having built anything. So it's important to be able to design conceptually. Here's the hoist, and here's the geared mechanism. That we explored these concepts before we actually built anything. In the synthesis step, you want to take all of the concepts and evaluate them. You want to estimate the preliminary feasibility of each concept. You want to establish metrics. From your performance specs, you want to establish metrics and use them to estimate the potential of each concept. A down selection usually occurs where some concepts are discarded or positive aspects of concepts are combined. The next step in the design process is the analysis and optimization step. This is where the detailed design is really done. During this step, you want to analyze and determine and prove that your device actually meets the performance specs that you've already established. Any optimization can be done here in order to improve the product before it's built. For example, here's the truck plate for the lift, the robot lift. This shows a stress analysis where we've put a fictitious load out at the very end of the robot lift. This is simulated 700-pound load in this area, and we're looking from the analysis of SolidWorks what the response of the truck is going to be. The yield strength for the material is approximately 36 kpsi. So you can see that the von Mises stress, there are some stresses that exceed this. So those stresses would have a factor of safety of actually less than 1. So that needs to be corrected. You can see some red areas here of high stress. This is a stress due to bending. Also a stress due to bending over here. There's some torsional stress here to worry about. These things can be fixed in this step. We can add some material here and change the geometry slightly so that we meet our performance spec of factor of safety. Another performance spec would be power. We want to make sure that the motor we put on there and that the gears, the various gear stages are adequate and we would be able to lift our 600 pounds. So what you could see here is that you start with the 600 pounds that you want to lift, and you think about some RPMs, and you think about the BHP is actually the brake horsepower, delivered horsepower that you need to have in order to lift the robot in its worst case situation. As you can see, I stepped back through and even considered efficiency here in order to figure out that the first stage worm horsepower needed to be 0.6. I found a first stage worm in order to accomplish this. At the input of the first stage worm is a second worm. And I also figured out what the specs of similarly, I figured out what the specs of the second stage worm needed to be. And I figured out what the motor torque rating needed to be and what the motor horsepower needed to be. Then I found a motor which could provide that, or the 3/4 horsepower at the 1750 RPMs, and the motor that had 27 inch-pounds. So all of these components working together would ensure that I'd be able to lift the 600 pounds in the required time. A final step after you've exhausted all possible theoretical analysis, of course, is to actually build the machine, make sure that it works. At this stage of the process, you could be ready for production, or there may be some iteration. I wanted to comment about the iteration, or the feedback loops. Each of the first 5 steps, there are feedback loops to any of the previous steps. I wanted to discuss that a little bit. Design process iterations. If you find a design flaw late in the game, you want to go back and correct it. Another thing is there may be some performance requirements that have been changed. For example, the 600 pounds for the lift that I had, the customer wanted to try a 300 pound solution as well. So the performance requirements can change. During the process, you may stumble upon a new concept, or you may find some other kind of design problem that you need to readdress. You may have some optimizations or improvements in the manufacturing process. It's important that your boss or your customer understands what you're faced with. You want to be honest with them and let them know when you find that there's a problem or an opportunity to improve the product. Here's a chart which shows Company A, the ideal effort, being front-loaded. During the design process, Company A puts a lot of effort into developing a really good product. They get all of the bugs ironed out before they start production. That is a successful company. In fact, it's Toyota. Company B, on the other hand, is an American car manufacturer. They don't put a lot of time initially into the design process. They wait until they start production, and then that's when they come in and have to fix the problem. So they're fighting fires all the time instead of designing quality products. There's a saying in the design process: fail early, fail often. You want to find and fix the problems that you have before production. You want to have the optimal product before you enter the production phase. So getting back to when you're ready for production, you want to make sure at the end of the evaluation that you have a solid product that can go and be produced. So now I hope you understand your role as a mechanical designer. Your value to your boss or your customer is greatly enhanced if you can do some simple things, like understand what the device needs to do, establish the performance specs, their values as well as what those specs are, create exciting concepts. You want to prove that your device meets the performance specs in the worst case scenario, and you'd like to do this without having built anything. You'd like to do this theoretically or analytically. And you want to convey these matters to your boss or your customer. Some good references for the design process courses: the Shigley Mechanical Engineering Design book, the Mechanical Design Process by Ullman, and also the Material Selection and Mechanical Design by Ashby. That concludes our presentation for today.